Welcome to the wonderful world of physics. This is the Chapter 16 homework for Physics 102B. We start with problem number 33. Two protons separated by 6.5 femtometers distance. What is the potential energy of this pair? You can see the equation for potential energy between two charges, K times the product of the charges divided by the distance. In this case, each of the charges being a proton is positive 1.6 times 10 to the negative 19 coulombs. You're going to want to include in a problem like this whether the charges are positive or negative, because that'll affect whether potential energy is positive, which means it's going to be repulsive, or if it's negative, that means they're attractive. Now in this case, it's positive. You plug in all the values and you get 3.5 times 10 to the negative 14 joules. Number 37. Find the potential energy of two charges located in the xy plane, and it gives the coordinates of those. Let's look at the picture here. Here I've drawn it on the coordinate plane. There's Q1 and Q2 in the coordinates that are shown, that are listed right here. When we do the potential energy equation, we're going to use this equation down here below my coordinate plane, K times Q1 times Q2 over R. Now we're given Q1 and Q2, but we need to know the distance. And so it helps to draw a picture here. We can see when we plot them out, the difference in the x is 0.24 meters, the difference in the y is 0.10 meters. We're going to use Pythagorean theorem. Now the equation I'm using is this, that the distance between any 2 points is the square root of the difference of the x's squared plus the difference of the y squared. But it helps to see it as a picture. So we plug in the difference of the x's 0.24 squared, the difference of the y's 0.1 squared, take the square root, and we get a distance of 0.26 meters. Then we plug that into the potential energy equation with the given charges, and we get a potential energy of negative 1.99 times 10 to the negative 7 joules. Number 41. Two protons released from rest 5 millimeters apart. Describe the subsequent motion after they're released. How fast are the protons moving when they're a great distance apart? Well, the subsequent motion is that since they are like charges, they're both positive, they will accelerate away from each other. Now, as they get farther away from each other, the force is going to decrease, so acceleration is going to decrease, but they will still be accelerating away from each other. To figure out what their speed is going to be at a great distance, and we can take that to mean an infinite distance, but it really just means a very, very large distance. Let's use conservation of energy. We'll take E1 to be the situation where they are 5 millimeters apart. E2 is going to be a great distance away. We have potential energy at 1, and there's no kinetic energy at 1 because it says they are at rest. So potential energy at 1 equals potential energy at 2 plus kinetic energy at 2. And we are concerned about that kinetic energy at 2 because that'll lead us to their speed. Let's plug in all the values. The potential energy at 1 is K times the product of the charges, so E squared divided by R1, and that R1 being 5 millimeters, equals potential energy at 2. Well, if we plug in K times E squared divided by a very large number, and I've just written there infinity, this becomes 0. So a great distance away, they have 0 potential energy. All of the energy has become kinetic energy. Kinetic energy is 1/2 mv squared, but keep in mind we're dealing with two separate particles, each of them having a mass of m. So we're going to say 1/2 times the collective mass, which is 2m times v squared. And now we clean things up, we simplify the 1/2 and the 2 divide out, and we're left with ke squared over r1 equals mv squared. Let's solve that algebraically for v. you should get Ke squared divided by R1m square rooted. There you can see I've plugged in all the values. And using the mass of a proton in kilograms, the charge of a proton in coulombs, the distance is in meters, 0.005, and in the end we get 5.26 meters per second. Number 43. At 1 meter from a point charge, the electric potential is 280 volts. What's the potential 2 meters from the same charge? And what are the magnitude and sign of the charge? I've written out the relevant formula that potential is kq over r from a point charge. R1 at 1 meter, V1 280 volts, R2 is 2 meters, and V2, that's what we want to solve for. If you take this original equation, it's good technique to get all the changing quantities to the left and the constants to the right. So V times R equals K times Q. And so we can write that down here. V times R is constant. Now we're not actually going to care, at least in part A, about what K times Q is. What matters is that V times R stays constant. So then we can say V1R1 equals V2R2. This will give us a relationship between the distance and the voltage without regard to charge. We're going to solve for V2. V2 equals V1 times R1 over R2. Plug in the values in the parentheses. I have 1 meter over 2 meters, so that's a 1:2 ratio. And we get that it's 140 volts. So notice that when the distance is doubled, the voltage is cut in half. Now part B is asking for the charge and its sign. So we'll go up to the original equation and solve it for Q. Q equals VR over K. And we can use either R1 and V1 or R2 and V2, either one. I prefer to use R1 and V1 just because it doesn't rely on information that I solved in part A. So just in case I did something wrong in part A, it's not going to throw off my answer in part B. So we get Q equals VR over K, plug in that information, and we get, you notice it's all coming out positive, so positive 3.12 times 10 to the negative 8 coulombs. Number 45. After walking across a dry carpet, there's potential difference of 4,500 volts between your hand and the doorknob. You reach toward the knob, a spark jumps, releasing energy of 1.6 microjoules. How much charge was transferred? Assuming all the charges were electrons, how many were there? All right. So the relationship between amount of energy and charge and potential difference is this, U equals Q naught V, where Q naught is going to be the total charge. We want to solve for that charge, so Q naught is U over V. It was 1.6 times 10 to the negative 6 joules over 4,500 volts, and we get a total charge released of 3.56 times 10 to the negative 10 coulombs. We want to know how many electrons there are. So let's multiply as if we're doing a unit conversion. 1 electron is equivalent to 1.602 times 10 to the negative 19 coulombs. So we do that division and we find that there are 2.2 billion electrons. Number 47. A 900 kilogram electric car uses a 270 volt battery pack. As the car accelerates from rest, 400 coulombs flows from the battery. What is the maximum speed the car can attain during this time? I've written the given information, the mass, the voltage of the battery, the total charge that flows, and we want to know the speed, the final speed, given V naught is 0. Be careful with your penmanship. Capital V, this is capital V right here, 270 volts, and these are lowercase v's. And even if your penmanship doesn't distinguish, as I've written it, there's not too much of a difference between my big V's and my little v's. Make sure at least that you can tell the difference when you are writing and reading your own work. The change in kinetic energy is the same magnitude as the change in potential energy. That's what I've done with the absolute value signs. I'm really not paying attention to positives and negatives here. It's the same magnitude, which is the charge times voltage. So the change in kinetic energy is the charge 400 coulombs times 270 volts, and that's 108,000 joules. So it's accelerating, it's gaining kinetic energy. Change in kinetic energy is 1/2 mv squared minus 0, because it started from rest. So we're going to take this equation, solve it for v, the velocity. We get square root of 2 delta k over m. Plug in those values and you get 15.5 meters per second. Number 49. The charmed lambda particle is a subatomic particle with mass 4.1 times 10 to the negative 27 kilograms and charge plus e. Find the potential difference needed to accelerate it from rest to 1% of the speed of light. There I've written out the given information. We want to know what voltage, capital V, is. Just as in the previous problem, change in kinetic energy is charge times voltage, and I've used absolute value signs because I'm not concerned with positive or negative. There's this understanding that it is gaining kinetic energy. So taking this equation, solving for voltage, that's change in kinetic energy over Q naught. Since it's starting from rest, change in kinetic energy is just the final kinetic energy, 1/2 velocity squared over charge. Plug in all those values, and you get a voltage of 1.15 times 10 to the 5th volts. Number 51, an ion passes through a 300 volt potential difference. It gains 9.6 times 10 to the negative 17 joules of kinetic energy. What is its charge? Repeat for an ion that loses the same amount of kinetic energy. We're not really told, we're not at all told whether it's positive or negative. So I start to draw a picture, and it says in the problem that it passes through a potential difference. And we can infer mildly that it's going up from 0 to 300 volts. That's a difference of 300 volts. Although the way it's stated, it's not really clear. It could be going from 300 to 0, going down through that potential difference. It's really a little ambiguous here. So here I've drawn the picture. We have the electric field line going from high to low, 300 to 0, and it's not clear to me as I read it whether it's going left to right or right to left in this picture. So the kinetic energy, the change in kinetic energy, the magnitude of it is the charge times the voltage. Now it says it's gaining that much kinetic energy, so it's definitely speeding up. Well, the charge is going to be change in kinetic energy over voltage. So I plug those in and I get 3.2 times 10 to the negative 19 coulombs. Now the other question, repeat for an ion that loses the same amount of kinetic energy. Well, the charge is going to be still 3.2 times 10 to the negative 19 coulombs. These two charges in part A and part B, they're going to be equal and opposite to each other. So they'll both be 3.2 times 10 to the negative 19 coulombs, but as I read this problem, I can't discern whether the first one was going with the electric field or against the electric field. So one of them is going to be positive, the other is going to be negative. It's just not clear from how the problem's written which is which. Number 53, the potential difference between a pair of parallel conducting plates is 65 volts. The plates are 3.2 centimeters apart. What is the magnitude of the electric field between the plates? And here we have the magnitude of electric field is the voltage difference divided by the plate separation. And so you plug in those values, 65 volts divided by 0.032 meters, and you get 2,000 volts per meter. Number 55, a pair of parallel plates produces an electric field of 850 volts per meter. An electron is released at rest from the negative plate. How fast is it moving when it hits the positive plate? 7.5 millimeters away. Here I've drawn a picture of the electric field lines going from left to right, positive to negative. So our electron is going to speed up going from right to left. It's starting at rest, V naught equals 0. What is the final V? And there are a few ways we can approach this problem. So let's look at my various solutions here. One way is to take that the change in kinetic energy, at least its magnitude, is the change in potential energy. They're actually going to be equal and opposite to each other, which is equal to Q times the voltage. The voltage is the electric field times the distance between the plates, E times delta X. So on the left-hand side of this equation, change in kinetic energy is 1/2 m times velocity squared, equals on the right-hand side, Q E times delta X. We solve for V, and that gives 2Q E delta X over M. We plug in those values, given that we're dealing with an electron, so we need the charge of an electron, the mass of an electron, and we get 1.5 times 10 to the 6th meters per second. So that's a good solution. Let me show you, though, there are other ways to solve this problem, and I have no preference between these ways. These are just in the order I happen to write them down. Another way we could solve this problem is to use more dynamics and kinematics. So we can start with F equals QE, and Newton's second law, F equals ma. So ma equals QE. And to know what acceleration is, we need to involve the displacement and the velocities. So come over to the right-hand side, a kinematic equation. V squared equals V naught squared, which is 0, plus 2a delta x. We solve for acceleration, which is V squared over 2 delta x. Take that value for a, plug it into this equation. Now we have mv squared over 2 delta x is QE. Solve it for V, and you notice we get the same value for V as we did up here in the middle of the page. Number 57. Two parallel plates separated by 6.5 millimeters have a potential difference of 250 volts between them. Find the electric field. What is the force on an electron in this field? All right, electric field is the voltage difference divided by the displacement, or the distance between the two regions. And so you plug in those values, you should get 3.85 times 10 to the 4th volts per meter. By the way, just to remind you, that could also be 3.85 times 10 to the 4th newtons per coulomb. What is the force on the particle, particularly talking about an electron? Force equals electric field times Q. So electric field times the charge, which is E. Now it's really negative E, so this comes out to be a negative answer, but that only tells us information about which way it's going. I'm really not specifying direction in this. We're just looking for the magnitude of the force, so I kept everything positive. And you should get 6.2 times 10 to the negative 15 newtons, or 6.2 femtonewtons. 59. Spherical equipotential surfaces surround a point charge. If the electric potential is negative 175 volts on a sphere of radius 0.65 meters, what is the charge? So we have the given information. We can say V equals KQ over R, but let's solve for charge. Q equals VR over K. We're just going to plug in those values. When we do, we get negative 1.27 times 10 to the negative 8 coulombs, or negative 12.7 nanocoulombs. Number 62. Suppose you want to make a parallel plate capacitor with square plates 1 centimeter on a side. How far apart should the plates be for a capacitance of 3 picofarads? Repeat for 3 microfarads, and are both designs practical? And we'll comment on that. So a side is 10 to the negative 2 meters, which means the area of that square is going to be 10 to the negative 4 square meters. Our capacitance is 3 times 10 to the negative 12 farads. What is the distance? We'll use the capacitance equation. We're assuming no dielectric in the middle. So capacitance equals epsilon naught times area divided by d. Solving for d, d is epsilon naught area over capacitance. Epsilon naught is 8.85 times 10 to the negative 12 times the area divided by capacitance. We get a distance of 0.3 millimeters. For part B, we do the same, but in the denominator is 3 microfarads, 3 times 10 to the negative 6 farads, so we get 0.30 nanometers. Now, on this fraction of a nanometer level, we're getting to the size of a molecule. So the question is asking, are these practical? And the one in part A is practical because you can have a capacitor, you can have this small distance between them, 0.3 millimeters is reasonable. To have a distance of the size of a molecule is much less practical. Number 63, we're given the capacitance, 250 picofarads, two identical circular plates, it gives their distance, find their radius. Reminding ourselves that area of a circle is pi r squared. So we have capacitance is epsilon naught times area over d. Let's substitute area is pi r squared. And we're going to solve this for radius. Radius then is the square root of capacitance times distance over the permittivity constant epsilon naught and pi. We plug in all the values and you should get 2.80 centimeters as a radius. Problem number 69 through 72 deal with 3 microfarad capacitors. Let's look at number 69 first. It says find the equivalent capacitance if the 3 are in parallel. And here I've drawn a diagram of that, 3 capacitors in parallel, all with 3 microfarads. And the formula for capacitors that are in parallel, their equivalent capacitance is you just add them up. So we have 3 plus 3 plus 3 microfarads, and that gives us 9 microfarads as the equivalent capacitance. Number 70 says the 3 capacitors in parallel are connected across a 30-volt battery. Find the charge on each capacitor and the potential difference across each. All right, well, we found in problem number 69 that their equivalent capacitance, when you put them all together, is 9 microfarads. And what I want you to remember is that capacitors in parallel all have the same potential difference. And so when they are hooked up to 30 volts across them, each one of them has 30 volts across it. So you can imagine there's maybe a battery down here and the current goes here and the battery raises up by 30 volts. And then you can imagine like pipes of water going down. Some goes down this way, some goes down this way, some goes down this way, but they all go down the same distance. So they're all falling down the same voltage, 30 volts. So each capacitor has 30 volts across it. The charge on each capacitor is given by Q equals CV. Charge equals the capacitance times the voltage across it. So 3 microfarads times 30 volts gives you 90 microcoulombs on each capacitor. Number 71, find the equivalent capacitance if the 3 capacitors are in series. To find the equivalent capacitance of capacitors in series, we're going to add the reciprocals, and that becomes the reciprocal of the equivalent capacitance. So the formula looks like this. So we can say that the reciprocal of the series capacitance is 1 over 3 microfarads plus 1 over 3 microfarads plus 1 over 3 microfarads, and you add them all together and it becomes 1 over 1 microfarad. And I recommend you go through the math on your own if I've done a little shorthand here, but show yourself, convince yourself that this actually works, because you need to be able to solve problems like this on your own. But so 1 over 3 plus 1 over 3 plus 1 over 3 becomes 3 over 3, so 1 microfarad to the negative 1. And then we'll take the reciprocal of that and find 1 microfarad. Number 72, the 3 capacitors in series are connected across a 30-volt battery. Find the charge on each capacitor and the potential difference across each charge. And the concept I want you to remember for series capacitors, capacitors in series have the same charge, which is also the charge on the hypothetical capacitor CS, or that equivalent capacitance. So let's imagine for a minute that there are not 3 capacitors here in series, but just 1 capacitor that has a capacitance of 1 microfarad, because that's what we got in problem number 71. So with our imagined 1 microfarad capacitor, the charge on it is its capacitance times the voltage, 30 microcoulombs. So this 30 microcoulombs is the charge that's on every one of the individual capacitors. To find the potential difference across each capacitor, use Q equals CV, but that becomes V equals Q over C. So it's 30 microcoulombs, which is the charge on 1 capacitor, divided by any one of those capacitors is 3 microfarads, and that becomes 10 volts. Number 77. For a defibrillator, it uses a 225 microfarad capacitor charged to 2400 volts. How much energy is stored? What is the power delivered to the patient if the capacitor discharges completely in 2.5 milliseconds? The energy stored in a capacitor is given by 1/2 CV squared. So we take capacitance times V squared times 1/2. You should get 648 joules. Then remember that power is energy delivered or energy transformed divided by time. 648 joules divided by 2.5 times 10 to the negative 3 seconds, and you get 259 kilowatts. Number 83, parallel plate capacitor. It gives the area, gives the distance. There's paper insulation between the plates, so find the capacitance, the charge on each plate when a potential difference of 12 volts is across the capacitor, and the maximum possible potential difference across the plates. We're going to use the capacitance equation that involves dielectric constant kappa. It says paper, we look up in the table in the book, kappa is 3.7. It'll be relevant to part C that the maximum electric field that can be sustained through the material is 16 megavolts per meter. So in part A, we use the capacitance equation. You can see I've plugged in all those values, and we get 8.868 times 10 to the negative 12. I'll say 8.868 picofarads. Once we have the capacitance, part B asks for the charge, and that's going to be the capacitance times the voltage. And in this problem, it says 12 volt potential difference. So there we have 1.06 times 10 to the negative 10 coulombs, or 106 picocoulombs. Then we want to know what is the maximum possible potential difference that can be sustained with this particular capacitor. So we're going to use now from the table the dielectric strength, otherwise known as maximum electric field, in the table. And as I look it up, it says for paper 16, and the units in that table are megavolts per meter. So 16 million volts per meter times 0.12 times 10 to the negative 3 meters, that's the distance, and we get 1920 volts. Number 85 says a 0.45 nanofarad parallel plate capacitor has plate area given. The dielectric has kappa 3.8, What is the plate separation? We're going to use the capacitance equation that includes the dielectric constant. We're going to solve it for D, and you see all the values that I've plugged in. And you get 1.27 times 10 to the negative 5 meters, or 12.7 micrometers. Number 91. A 0.01 microfarad 300 volt capacitor costs 25 cents. A 0.1 microfarad 100 volt capacitor costs 35 cents. And a 30 microfarad 5 volt capacitor costs 88 cents. And it asks in parts A, B, and C a different competition between the three. Part A asks which one can store the most charge, B, which can store the most energy, and C, which is the most effective as an energy storage device in terms of energy stored per unit cost. So it's very necessary, as with most physics problems, we write down all that given information, so we're not trying to pick it all out of the paragraph. So I've written the given information at the top, the capacitance, the voltage, and the cost. Now, for part A, it wants to know what are the charges. It's actually asking which one can store the most charge, but the way we'll go about that is to see what each of their charges are. Charge on a capacitor is the capacitance times voltage. So let's, as always, be mindful of units. Since they're all given in microfarads consistently and volts, I'm not even going to bother to convert to MKS units. That's one unnecessary step that with each step you take, you're prone to making an error. And so I always want to reduce the number of unnecessary steps. Let's just leave it in microfarad volts instead of farad volts or coulombs. So we multiply them. 0.01 microfarads times 300 volts gives 3 microfarad volts, which, by the way, is microcoulombs. The next one is 10 microfarad volts, which is 10 microcoulombs. And the next one, the 30 microfarads times 5 volts, is 150 microcoulombs. In the end, because the units were consistent, it doesn't really matter to us what the units are. We're comparing the numbers 3, 10, and 150. And 150, so the third one is the winner in that competition for which one can store the most charge. Question B asks about the energy. 1/2 capacitance times voltage squared. So we plug each of those in. Again, I'm not going to worry about MKS units. I'm just going to be concerned with keeping units consistent. When we multiply out for the first capacitor, it's 450. The units become microfarad volts squared, which is actually microjoules. The second one is 500 microjoules. The third one is 365 microjoules. So 500 is the winner. The second capacitor can store the most energy. Then we're looking for energy per cost. Well, in part B, we solve for the amount of energy. Then we're given the cost, so we just divide. We're going to get our answer in microjoules per dollar. And when you plug those in, the first one is 1,800 microjoules per dollar. The other one, 1429 and 426. So capacitor number 1 is the winner in terms of energy per cost. Question number 92. Camera flash tube requires 5 joules of energy per flash. The flash duration is 1 millisecond. What power does the flash tube use while it's flashing? If it operates at 200 volts, what capacitance is needed to supply the flash energy? And C, if the flash tube is fired once every 10 seconds, what's the average power consumption? So part A, the power is energy over time, so 5 joules over 10 to the negative 3 seconds, 5 kilowatts. Part B, we want to know what is the capacitance needed for that amount of energy. So U equals 1/2 CV squared becomes C equals 2U over V squared. Plug in those values, we have 200 volts, and we get 2.5 times 10 to the negative 4 farads, or 250 microfarads. Question C then talks about average power consumption over a long duration. So we're using this flash once every 10 seconds, presumably maybe for several minutes on end. Well, so it's going to be 5 joules every 10 seconds. So the average power, 5 joules divided by 10 seconds, is 0.50 watts. Now notice the difference between point A and C, or part A and C. Part A is referring to during the moment the flash is actually lit. For that brief microsecond, 5,000 watts. But part C is looking over a long duration. Most of that time, it's going to be dark. It's only bright for a thousandth of a second, a millisecond, and then it's going to be dark for the rest of the duration. So the average power isn't going to be nearly as much as in part A. Question number 98. A neuromuscular microstimulator, a device designed to be implanted into paralyzed muscles or other tissues suffering from neuromuscular dysfunction. It supplies an electric current that stimulates the dysfunctional tissue. A particular device uses a capacitor built into a microchip. The capacitor can supply 10 milliamperes of current for 200 microseconds before it's fully discharged. Find the initial charge on the capacitor and the capacitance if it's initially charged to 4.5 volts. So we have a current of, it says 10 milliamperes, so that's 10 to the negative 2 amperes. The time, it says 200 microseconds, so 200 times 10 to the negative 6, or 2 times 10 to the negative 4. The total charge then is current times time, and you get 2 times 10 to the negative 6 coulombs, or 2 microcoulombs. Part B relates capacitance to voltage and charge. We want to know the capacitance. And it says it's initially charged at 4.5 volts. With that in mind, we can say the charge is 2 times 10 to the negative 6 coulombs, which is what we got in part A, divide by 4.5 volts, and we get 4.44 times 10 to the negative 7 farads, or 444 nanofarads. That is the end of the Chapter 16 homework. Have a great day.